Welcome to lesson 2 on chapter 5, all about radians. This time we're going to look at calculating the arc length and the area of a sector. And we're also going to look at the area of a segment. Okay, so the arc length, the area of a sector, and the area of a segment. Okay, so there's some key words in there already that I've highlighted in bold. You're going to need to be familiar with trigonometry for this lesson from your GCSE work and all the trigonometric ratio and identity and equation work from last year. All right, I've also included, same as last lesson, 2 really important formulae that we're going to be working with today. So that's the arc length of a sector and the area of a sector given below. Right, so let's get started. Could you please pause the video and try the 4 warm-up questions? All right, and let's have a look at the solutions. So for question 1 in the warm-up, it asks you specifically to use the cast diagram, okay? Now, we're not allowed to use calculators for this. We have to use the cast diagram. To do that, we saw in the previous lesson, probably the easiest way to do this would be to convert it into degrees, because we're probably not yet comfortable with using radians at the moment. Remember, of course, I can use a straight swap. If I see a pi anywhere, to convert that into degrees, I can simply use 180. All right, so I can rewrite this tan calculation as the tan of 9 multiplied by, okay, put it in 180 degrees, and then divide that by 4. Okay, and that simplifies to tan of the angle 405 degrees, which is outside of our usual range, but we can find the tan of it nonetheless. Right, now we have to use the cast diagram for this. So that's not the answer. We've just converted that into degrees. On our cast diagram, we're just going to draw it over here. Let's see what we get. So just to label it carefully, remember that we start at 0 degrees and we go in the anti-clockwise direction for positive angles. Okay, and we'll just put on all the other important reference points here. We've got 90 degrees, we have 180 degrees, 270, and remember, of course, this comes back to 360 degrees here. Okay, now we're finding the tan of 405 degrees. Now, what this means is we're going to go 1 full turn all the way around. So that's a full 360, and then I've got to go a little bit more. Now then, if I add the 90 degrees to the 360 degrees, that's going to give me 450 degrees. Now, this angle is a lot less than that, so it's going to be somewhere in this quadrant. Okay, I'll put it about there. Okay, so this angle is 405 degrees. Now, what angle does that make with the horizontal? Well, a little quick subtraction there. If we do 405 and subtract 360 from it, you'll quickly realize that this is a very familiar angle, and we get 45. That's 45 degrees. Okay. Now, what we haven't done yet, we haven't labeled our cast diagram. So remember, its cosine is positive there. All angles or all trig ratios are positive there. Only sine and then only tan. So from the cast diagram, we can see very clearly now that the tan of 405 is simply equal to the tan of 45 degrees. Okay, because in quadrant A, tan, sine, and cos are all positive all the time. We need to find out what tan of 45 is now. Now, if you don't remember this, remember from a right angle triangle of 45 degrees, 45 degrees there. Now, if we do an angle sum, we know that this is going to be 45 degrees as well, which makes this an isosceles right angle triangle. Okay. Now that's important. Now suppose that each of these has a side 1. Okay, they both have to match. If I find the tan of, let's say, this 45 degree angle here, it doesn't matter which one I choose. So just say the one I've just arced off there. Okay, we can see that if I take the tan of that angle, I'm just going to get 1 over 1, which is 1. And it doesn't matter what I choose for these lengths. Okay, they're always going to be the same because it's isosceles. So the tan of 45 degrees is 1. Okay, so that was quite nice. Moving on to question 2, we have the same idea. So we're going to find the cosine of negative 2 pi over 3. So first of all, convert this into degrees. Now I'll do this a little bit quicker. I'll assume you've done that. Okay, if we convert that into degrees, you're going to get negative 120 degrees here. Okay, once you've subbed in 180 for pi, which is here. So 2 multiplied by 180 divided by 3, and it's the negative version. And then we can draw the cast diagram for this one. Now notice this is negative. So if we start at 0 degrees, I wish to move in the negative direction that way. Okay, so my first stopping point would be negative 90 degrees. Okay, and then negative 180 degrees. And I know that my angle is going to lie between negative 90 and negative 180. It's going to maybe somewhere there, probably not that far actually. Let me just undo that. Something around about here. Okay, so that angle there is negative 120 degrees. The question is, what angle does this make with the horizontal? So what is the difference between negative 120 and negative 180? Again, I'll assume you've done that. It's of course 60 degrees. Okay, that angle is 60 degrees. So we now have an acute angle to work with. Let's add this to the first quadrant. So we're going to put the 60 degrees on here. Okay, and one thing I've forgotten to do is to label the quadrants. So it's C, A, S, and T. So notice that negative 120 is in the tan quadrant where tan is positive. So we know that this value here must be a negative. Okay, it's a negative value. And we also know that in the acute section where all are positive, this must be, the cosine of that angle must be positive. So the only way to reconcile this is if we change the sign. So this must equal negative cosine of 60. Because if we ignore the sign, we know that the value of cos 60 and the value of cos 120, even though it's negative, will give you the same value, but with alternate signs. All right, so we just have to make sure that the signs are correct. Okay, and cosine 60 is something we are familiar with as well, and it's the negative version. So this must equal negative 1/2. I hope I made that clear. I'm not sure that I did. Okay, but don't worry too much about that again. Once again, you'll be able to use calculators in the exam. And for question 3 of the warm-up, we have to calculate the value of theta here. Now we're given the 2 radii of our sector, and we're given the arc length. So let's just make a little list of the things we know. Okay, so we know what r is. R is 5 centimeters. Okay, we know the arc length L is pi centimeters, but we don't know theta. So theta is the thing we wish to find. Okay, so we're going to use the arc length formula because we have r and L and we wish to find theta. So if I just write it out, L is of course theta divided by 360 degrees multiplied by, sorry, let me just undo that. Divided by 360, so theta degrees divided by 360, and then multiply that by 2 pi r. Okay, let's sub everything in. So pi goes in on the left, so pi, that's equal to the thing we want to find, theta over 360, multiplied by 2 pi, and then r is of course 5. So we're going to multiply that by 5. Okay, let's just tidy this up now. So we've got pi is equal to, now I can write this as one fraction. So I can write this as 10 pi, which is this part, multiplied by theta degrees divided by 360. Okay, now you can do this many different ways. You'll notice as well that the thetas here are going to cancel. Sorry, I beg your pardon, not the thetas, the pi's are going to cancel. And I've also got a bit of cancellation here with the 10 and the 360. So there's lots of cancelling going on. So let's just do it bit by bit. So I'm just going to move across to here. So I've got a bit more space. So I'll cancel the pi's out. So this is going to be 1 is equal to 10 theta degrees divided by 360. And then if I cancel down that, we get 1 is equal to theta degrees over 36. And there's our answer revealed. Okay, so therefore theta degrees is equal to 36 degrees. Okay, so that's that one. Now on question 4, we have a similar situation. We're given 3 measurements, the radius, which is the same for both because it's a sector, and the arc length pi over 4. All right, let's do this. So let's just make a list of what we know. So we know the radius in this case is 4 centimeters. We know the arc length is pi over 4 centimeters, given exactly. Our job is to find the area of the sector. Now you'll know from the formula, to get the area of the sector, it's the angle over 360 multiplied by pi r squared, the formula for the area of a circle. It's a fraction of the area of a circle, isn't it? So I'm going to need theta, okay, because I don't need to substitute in the arc length, but I do need to substitute in theta. That's really important. So I need to find theta before I can use this formula. So theta is the missing thing. So let's put theta here. And can I find it? Well, we're going to have to use the arc length formula first. So I hope you've got enough room for this. So the arc length formula, I won't write it out again. So we have pi over 4 would be equal to theta over 360 multiplied by 2 pi r. So it's going to be 2 pi multiplied by r, which is of course 4. And we just have to make theta the subject and look for any cancellation. So what I'll do, again, I'll write it as a single fraction. So this is going to be 8 pi theta over 360. Okay, if I multiply across and divide, we're going to get theta is equal to 360 pi divided by 8 multiplied by 4, 32 pi, like that. Okay, so the pi's are obviously going to cancel. All right, and then the 360 over 32 is going to simplify. And we are going to get theta is equal to 11.25 degrees. So we've got our theta. So this angle here is 11.25 degrees. So now we need to find the area of the sector. So I'll just partition the screen. Let's write it out. So the area is going to be theta, which is 11.25. I've just found that. Divide that by 360 and multiply it by pi r squared, which is pi multiplied by r squared, which is 4 squared. Okay, and on your calculator, you can do this. So A is, of course, going to be rather nicely in terms of pi over 2. And that's going to be centimeters squared, making sure we've got the units on there. All right, and then we're finished. So in this section, we're going to look at the arc length and area of a sector formulae that you have been using since GCSE and have been included so far in the definitions at the start of each lesson. Okay, so the arc length, L, defined as theta divided by 360 degrees multiplied by 2 pi r. Now, just a note on this, and I don't think I went through this particularly convincingly in the warm-up. The angle theta is measured in degrees, okay? Now, notice that the degrees units will cancel, okay, as a fraction. And r is measured in centimeters or meters or whatever units are specified. So this will give you an arc length in those units because the degrees will cancel out, okay? And it's the same thing over here. Now, in a moment, we're going to convert these formulae so we can use them when we've got angles defined in radians. So just to remind you of this, we need to be clear about what a radian is. So in degrees, 1 radian is 180 degrees divided by pi. Okay, and that's the equivalent of 1 radian. Now, how are we going to adapt our formulae? Well, we can do this directly. We can derive these new formulae, and you'll see how much more simple it is to use radians. So before we begin, I've just given you the formulae for the arc length and the area that was specified above, so we can see it in plain sight. And remember, we're going to write this for radians rather than degrees. So I'm just going to write a reminder here. Remember that pi radians is equal to 180 degrees. That's basically all you need to know. Okay. Now we can do a little bit of direct proportion here. If I multiply both sides by 2, which we've done already, we can see that we're going to get 2 pi radians equal to 360 degrees. All right. Now that we know that, I can now do a straight swap between the 360 degrees given here, okay, and the 360 degrees that we can see in the formula over there. And that's all you need to do. So let's just make a note of what we're doing, just so we're clear. Okay, so we're going to replace 360 degrees with 2 pi radians. And you can just write it as 2 pi. It's absolutely fine. All right, so that's really important. Okay, so this is key. So let's sub it in. So in the formula, we're going to have L is equal to theta divided by, I was doing it in a different color so we can see it. So theta divided by 2 pi. All right, now remember, now theta is going to be an angle defined in radians now. So if I wrote radians here, theta would be in radians, the 2 pi is in radians, the units will cancel. All right, so this arc length is still going to be in centimeters or meters or whatever unit of measurement we're using. Let's multiply that by 2 pi r now. And what you'll notice is, which is rather nice in this situation, okay, we have some really nice cancellation. So the 2 pi here in the denominator will cancel with the 2 pi here, which means that if we state an angle in radians in a sector, the arc length of the sector is just literally going to be the angle multiplied by the radius, which we write as r theta. Okay, so this is the new formula for the arc length, and look how much more simple it is. Okay, so make it look important. Okay, this formula, because we're going to be using it a lot. Okay, so that's our new formula for the arc length, and we use the same, it's not a trick, but we use the same substitution for the area. So we can just replace the 360, which we can see here, with 2 pi. And I'll suggest that you pause the video and do this as an exercise yourself and see what you get for the area. Okay, let's have a look what it is. So the area, so therefore the area is now going to equal theta divided by, and we're going to put the 2 pi in. Okay, and then we're going to multiply that by pi r squared. All right, now we have a little bit of cancellation here. The 2's won't cancel, but the pi's will. So the pi is going to cancel here and here, and we can tidy this up really nicely. So the area is going to equal, now we've got a 2 in the denominator. I'm going to bring it out to the front as a half. And then we've got r squared multiplied by the angle. Okay, good indication of an area formula having a squared measurement like that, which we used to do in dimension analysis, which we don't do anymore. Okay, so if we put that in a box, make it look really important, again, you're going to be using that quite a lot. So these are our new formula. Now, obviously, the important thing is that we have our angles in radians, okay, at all times. If we use these formulae and our angles are not in radians, then we're going to get the wrong answer. So I'm going to make a serious point about that when we do the examples. Okay, right, let's move on to the next section. Now, for the worked examples we're going to start with, we're just going to do some basic substitution into the formulas we've just derived. Now, if we just read the question, there's a few words here we're going to need to be familiar with. So it says the arc of a circle AB. Now, that means that the arc part of this diagram that I've pre-drawn could start at A and end at B. Okay, it doesn't matter which way around you do it, but that's what it means. So that's the arc of a circle AB. If we just look further along, because we know it's an arc of a circle, we can join the ends of the arc to the center of a circle, which we can see over here is called O. Okay, so that means that we can just label this this point as O here. All right, and that means that the length OB and OA are the same, which is just a radius, which is given to us in the question. So that's going to be equal to 5.2 centimeters. Okay, so this measurement here is 5.2 centimeters. And because it's a radius and it's a circle, they're both the same. Well, it's an arc of a circle, isn't it? And we've created a sector as well, OAB, which has an area. Okay, so we've dealt with the 5.2 centimeters. We know it's an arc of a circle center O. And then we have this word subtends. Okay, now I'm just going to highlight that. You'll see that a few times. Okay, subtends an angle. So this is the angle opposite, if you like, or the angle between the two radii. So we know that is 0.8 radians. Okay, so this is 0.8 radians, this angle here on our diagram, 0.8 radians. Now we're going to calculate the length of the arc AB. Well, we have a new formula. Let's write it down. Our new formula, the arc length is just r theta when theta is in radians. Okay, just as a reminder. Now, if we just sub in the values, this means that the arc length is just going to be r multiplied by 0.8. So it's 5.2 multiplied by 0.8. And if you do that, you're going to get 4.16 centimeters for the arc length. I mean, it couldn't be simpler, could it? I mean, what a great formula this is. Okay, so we can answer questions really quickly now without using probably a slightly more complicated formula that you actually learnt at GCSE. So this is part A, complete. Now for part B, we're going to look at the area of the sector OAB. And it's straightforward again. We're just going to substitute everything in that we know. So for part B, so I'm just going to leave room for the calculator in a second. So for part B, we're going to have the area is equal to 1/2 r squared theta. All right. Now this is going to equal, let's sub everything in, 1/2 multiplied by r, which is of course the radius here. Okay, so that's going to go in. So that's 5.2 squared, and then multiply that by the angle, which we know, of course, is 0.8 radians. So I'll just put that in as well. Sorry if I'm just over egging it a bit, but might as well get these right. So multiply that by 0.8. Now, you don't need your calculator set to radians on this. If you want to know how to set your calculator radians, there's a separate video on that. So I'm just going to bring up the calculator now, and let's have a look at what this calculation actually is. I'm just going to move it a little bit if I can. Is it going to move? No, never mind. So I'm just going to have to erase some of this. It's in the way. Okay, so let's use the calculator. So it's at half, so it's going to be 0.5 multiplied by 5.2 squared. Okay, multiplied by 0.8. And that's going to give you that fraction. We can convert that into a decimal. So that's going to be 10.816. This emulator, by the way, it uses a comma instead of a decimal point, which can be a bit confusing. So this is going to be 10. Now we'll do it to 3 significant figures. That's going to be 10.8 centimeters squared to 3 significant figures. All right, so I think that's all pretty okay, pretty straightforward. We're going to have to adapt this, aren't we? This is an A-level course. We're going to have to bring in some problem solving, which we're going to do next. So in worked example 2, we're going to introduce some problem solving. And this is a question that you might see in an exam. Okay, so let's just read through the information that's been given and see what we can do with it. So it says the diagram shows a sector AOB. So we have that of a circle with center O and radius r centimeters. Yes. Now the angle AOB is in radians. Okay, that's important. Okay, it's in radians. So this angle here is in radians, and the area of the sector AOB is 50 centimeters squared. Let's make a note of that. So the area of the sector AOB, we have been told, is 50 centimeters squared. So I just like to build up a summary of information here. Okay, that's dealt with the first two sentences. Now, there's some important information in the third sentence. Okay, I'm going to highlight this because this is really important. It says, given that the perimeter of the sector is twice the length of the arc AB, find the exact value of R. Right. Now, it says specifically the perimeter of the sector. Well, okay, we can work out the perimeter of the sector. And we also mention here the length of the arc AB. Well, let's deal with the length of the arc AB first. Okay. So we're going to call the arc AB, using what's given in the formula. We're just going to call it L because that's what we use. So we're going to call this length L. All right, so my arc AB, I'm just going to put a note under there as well. We're going to call that arc AB L. Now you'll notice we can actually find out what the perimeter of the sector is. Okay, the perimeter of the sector. We just have to go for a walk around the sector. So the perimeter of the sector, let's make a note of this as well, of the sector AOB is equal to, now let's just go for a walk around the object. So we start here, that's R plus L plus R. Let's write that in. So it's going to be, oops, just undo that. It's going to be R plus L plus R, which is of course equal to 2R plus L if we collect the R's together. So this is the perimeter of my sector. Now that means I can write the perimeter as 2R plus L there. Now if you notice that sentence, it says given that the perimeter of the sector is, so in other words, is equal to, is twice the length of the arc AB. So twice, obviously 2, and then 2 lots of twice the length of arc AB, so 2 times L. Now this has given us an equation, okay, with 2 unknowns. So let's write down what this has told us. So from the information given, we can now say that the perimeter 2R plus L, which we found by going for a walk around the sector, is equal to twice the length of the arc AB. So in other words, 2L. Now this is the key to unlocking this problem. We can collect the L's together. Notice I can subtract L from both sides here. So if I take L away from both sides, I'm going to be left with 2R is equal to L. Now, that's really good. This means now that we can express the arc length in terms of the radius. A bit like what we saw in the warm-up question when we defined a radian for the first time. So I'm going to replace this L, or I can replace this L if I like, with 2R. Okay, they're the same thing. Now, what can I do with that? It's the exact value of R that we need, and we know the area. We haven't used this information here yet. Okay, we haven't used this information. Okay, so let's write down the formula for the area of a sector. So the area of the sector AOB. Okay, well, we know it's 50 centimeters squared, but we also know that the area of a sector is going to be 1/2 R squared theta. That's given to you. Oh, what's what we derived earlier must be equal to 50. Okay, using that information up here. Right, what can we do with this? Well, theta is in radians. R squared, well, that's what we need to find. We need to somehow remove this theta from the equation. This is causing a problem. Okay, how do we remove theta from the equation? Well, we can use what the step above. So I'm just going to go back to this. Remember, this is the arc length, L. So we know from the formula that L is equal to R theta. Okay? So therefore, 2R in this case must be equal to R theta. Now, isn't that fantastic? Now the R's are going to cancel. So the R here and the R here are going to cancel. So that means that our angle theta must be 2. Okay, that's really good news. So we now know that theta is equal to 2, or 2 is equal to theta. So we can now put this into this equation now. Okay, and then we're nearly there. All right, so we now know that, therefore, 1/2 R squared multiplied by 2 is equal to 50. Which implies, if we just notice that the 2's will cancel. Okay, we have 1/2 multiplied by 2, so 1/2 and 2, they are going to cancel. So we just get that R squared is equal to 50. So R squared is equal to 50. Now we need the exact value. It says the exact value of R over here. So I'm going to have to write this in surd form. So that implies that R is equal to root 50. But we can do better than that, can't we? If we simplify the surd, remember that's 25 multiplied by 2, all in a square root. So this is going to be 5 root 2, and your calculator will also do that for you. And that's centimeters. So that's the final answer. Okay. Now, let's just recap. There's a lot going on in this question. So let's just recap. I took all the information from the first 3 sentences, and we managed to get to this point here where we had this expression. And then I could use the formula for the arc length to find the angle theta, which is here. Okay, now once I got the angle theta, I could then substitute that into this equation here. And I know this equation holds because we were told the area of the sector earlier on. Okay, so it's putting all the pieces of the jigsaw together. Now, there is a slightly alternative way of doing this. And I'll say slightly, but it's something you might have considered, having maybe done this yourself. So I'm just going to put an alternative approach here. Now, you'll notice we know that L is equal to R theta, okay? And we also know that the area is equal to 1/2 R squared theta. Now, we can actually express the area in terms of the arc length if we wish, because we can write the area as follows. We can write it as 1/2 multiplied by R multiplied by R theta. Okay? Now, it's a strange way of writing it, but remember, R squared is just R multiplied by R. And what I've done there is I've kind of drawn your attention to this R theta here. Now, notice the R theta is just L. So I can actually write the area as 1/2 R L. Okay, now that could be quite useful. So and strangely, it's the radius times the arc length divided by 2. Okay, now if we know that, then from this question, we get to the point where we know that L is equal to 2R. And you don't have to find theta anymore. We can just substitute that directly into this equation or this formula here. Okay, so therefore you would get 1/2 r multiplied by 2r, which is just going to be r squared. And that would be the expression for the area, which of course is equal to 50. So you get to the same result. So for worked example 3, which is our final worked example, there's a couple of pieces of information I need to go over before we attempt this. The first is to do with circles. Now, I've drawn a circle here and I've divided it from 2 points on the circumference. And notice that these 2 points on the circumference don't allow for this line to pass through the center of the circle. Okay. Now, this has a special name, as you may be aware. This is called a chord. All right. So this line, we know this as a chord. Okay. So I'll just make a note of that. So a chord is a line that splits the circle into 2, but not through the center of the circle. So it's not going to produce 2 semicircles, in other words. Now we need a name for what we've split our circle into. All right. And then we can do this if we just sort of highlight this part of the circle here. Okay. So that's the smaller piece that I've cut using my chord. And this has a name. This is called the minor segment. Okay. So I'll just make a note of that. So this is called the minor, as in smaller, so minor segment. So we've split our circle into what we call segments because it's not cut through the center of the circle, okay, in any way. A sector, of course, is what we think of like a slice of cake. So it's cut along the radii from the circumference to the center and then back out again. The other part of the circle that we've got left over, the bigger piece, this is called the major segment. Okay. So it might be worth to note this down on this example in case you've forgotten. The second piece of information we need to know is the area of a triangle. Now I've drawn a triangle here, ABC, and we can label the sides. You may be familiar with this from GCSE and perhaps earlier. So if I've got my my vertex A here, then the side opposite that vertex we can label with the lowercase version. So that's going to be little a. Okay. And then similarly, if we go around the triangle, this vertex B here, well, I can label the opposite side as little b. And then my vertex C here, I can label the opposite side as little c or lowercase c, which is more exact. Okay. Now, suppose I wish to find the area of this triangle. All right, so let's just have a go at that. So recall, right, so the area, well, there's a few different ways I could do this. Okay, so my area, I could say, all right, I could take the angle A here. All right, so that would be 1/2. And then you multiply, so that's the angle subtending the two sides B and C. So that would be 1/2 BC multiplied by the sine of the angle that subtends them, between them, if you like. There's another way I could do it, though. All right, I could take my angle B up here and use that to calculate the area. Now, if I did that, okay, it would be 1/2 again. Now, the two sides that my angle subtends, this is going to be AC sine B. Okay, and I think you've probably seen the pattern. And then the final one, let's take the angle C. Nothing to do with an island just off the north of Wales. Sorry about that. Okay, so that's going to be 1/2 And the two sides on either side of that angle are A and B. And then we take the sine of the angle C. So there's ways of doing that. Now, it depends which angle you have, of course, but it's an equivalent method. Now, what we're going to do in this question is we're going to use this information to prove this formula that is given here for the area of the minor segment. Now that it's shaded in yellow, or it'll be black and white on your notes unless you printed them out in color. So maybe just highlight that segment A if you like. So how do we do this? Well, what we could do is I could just create a couple of images and hopefully you can see how this works. So I'm going to first of all, I'm going to draw another circle like so. So we can take a circle like that. Now I'm just going to reproduce what this diagram is giving us. So we've got the center of the circle here. Okay. Now this is the point Q. This is the point O, which is the center of the circle, and this is the point P. All right. And then we know that it's got a radius of R centimeters and an angle of theta, okay, measured in radians at the center. Now, this will create a sector, okay? So if I just shade in all this, this is a sector. How do we find the area of that sector? Well, the area of the sector is quite simple. We've just been doing this quite a lot. So the area of the sector, OPQ, is going to equal just the formula, isn't it? 1/2 R squared theta. Okay, because we're using the same symbols to represent the radius and the angle. Right, but I don't want the area of the sector. I want the area of the segment. Now, what I could do is, what if I just superimpose the triangle OPQ over the top? So if we go back to this diagram here, you can see that there's also a triangle OPQ, okay, which is this triangle here. All right. Now, if I add that to my diagram, so this is going to be OPQ like that. What's the area of that triangle? So it's got the same name, but it's a triangle, isn't it? The area of the triangle OPQ. Now, if it's not very clear, I could just redraw it here so you can see it more clearly. That triangle has an angle theta at the middle and a radius of R centimeters. Okay, now because it's the radius, I can also write the radius here as well. So that's R centimeters. And I can use my formula that I talked about a few minutes ago. Now, it doesn't matter which one I choose because the two sides are like BC, AC, or AB. It doesn't matter. The two sides are going to be R in all cases. And the angle is always going to be theta. So in other words, the area is going to equal 1/2. Then I've got my two sides, which I'll just highlight. So I've got my two sides, which are both, excuse me, let's undo that. Two sides, which are both R, and then my angle in the middle, which is theta. So I can write my area of the triangle as 1/2 R squared sine of theta. Okay, using the triangle formula from earlier. I hope that's okay. Now, how do I get the area of the segment A? Well, the segment A on this diagram is this part here. So what I'd need to do is I'd take the area of the sector. So let's write this down. So the area of the segment which is called A, would be the area of the whole sector, OPQ. Yeah, the larger area. And then I just subtract the area of the triangle, OPQ. I'd have to take that triangle away from the area of the sector, and what I'd be left with would be the segment A. All right, so let's sub in what we've found. Now, remember, we've just worked these things out. So I know that the area of my sector, OPQ, is this. And the area of my triangle, OPQ, is all this. Okay, so I just subtract them. Now let's see what we get. I hope that makes sense. So this is going to be a half r squared theta subtract 1/2 r squared sine theta. They're very similar, aren't they? Okay, now we haven't quite got the formula that I wanted. Now it looks like there's a half r squared factored out. And you can see here, we can factor out a half r squared from both of these terms. Okay, so I'm fully entitled now to write down that final version. So this is rather nice. So we get 1/2 r squared, open a bracket, and then we'll have theta subtract sine theta. Okay, and that concludes this example and this lesson.